And since you have done the homework, so we don't need to review much, but probably remember that we learned about crystalline structure of metals, and we learned that it is very related to theoretical density. And the formula, we looked at the formula together, and we did one example. And you have done one example in the homework that you just handed in. So it turns out that, as you would expect, the crystalline structure has a lot to do with the density. And because metals are very closely packed, very densely packed, they tend to have the largest density among the different categories of materials. Ceramics are next. They are not as closely packed, densely packed, followed by polymers and composites. Of course, within each category depends on the exact crystalline structure, etc. But these are not really crystalline, and you can see the difference in density. So it's kind of cool that just by looking at the crystalline structure, you can predict the macroscopic properties like density. So that's kind of the take-home message. There is one more example that I have, and to warm up, and this is Friday before spring break. Let's do this one example also together. So copper, this is about copper, has an atomic radius of 1.28, that's angstrom. What you see, the symbol, if you forgot, this is 10 to the minus 10 meter. So the nanometer is 10 to the minus 9, and angstrom is 10 to the minus 10. And copper has FCC, crystalline structure. Atomic weight is given. So you are asked to calculate the theoretical density and compare it to the measured density, which is 8.94 gram per cc, and cc is the same as centimeter cube. This should be just easy. Be careful about the units. Anyone has some numbers? one correct answer. What I have is around 8.89. Or you may have it something like it's quite similar to the value that is given. I can see that. This is a straightforward. This was just a warm-up. And here, this is just a table which gives you a kind of an overview what material has what type of crystalline structure. Remember BCC, HCP, FCC, and also the atomic radius is given in terms of nanometer. In case you forget, this is 10 to the minus 9. This is a summary for different materials that you can take a look at. Before solving a few examples, there are a few things that I like to tell you before solving a few examples from fundamentals of engineering exam. One is that sometimes the same material, if you heat it up, it will have different crystalline structure. This crystalline structure evolves. So here you have iron. Depending on the temperature, it can have BCC, FCC, or BCC crystalline structure. This is called polymorphism. Means that the same material may have different crystalline structure depending on, for example, in this case, depending on the temperature. And then to distinguish these different phases, we use these Greek letters like alpha, gamma, delta. So these are different phases of the same material, and they have different crystalline structure. Another important thing is that the materials may just have one crystal. They may be single crystalline structures, like what you see here. But most materials that we are interested in, like aluminum or steel, they have these polycrystal structures. It means that you have different crystals next to each other. We'll talk about this a little bit later in more details. But this is important in terms of material properties, especially in terms of anisotropy and isotropy. Is there someone who wants to define for me what isotropic material is? You should have seen this before, yeah.
Same in all directions.
Exactly. So if the material has the same properties in all directions, it's isotropic or isotropic. If it doesn't, it's anisotropic. Now, if the material has only one crystal, depending on the direction, for example, here you see, if it is in this direction, it only crosses two atoms. If you go in the other direction, this is a body-centered cube crystal, you cross three. And then you will have two different stiffness in two different directions, to put it very simply. So if the material is single crystalline, a lot of times it's anisotropic. The property is different from, depending on the direction. If you take this direction, you have fewer atoms to break apart or to pull apart when you apply the load. If you apply the load in the other direction because you have more atoms, then you need more force. So stiffness would be different in one direction compared to the other. So you have anisotropy. In contrast, polycrystalline materials, depending on the grain distribution, you can have isotropy or anisotropic property. If the grain distribution is very random, it will be isotropic. If it is not random, then you are going to have anisotropy depending on grain distribution. This is actually very important in a lot of applications. So in some engineering applications, we really look for single crystalline materials. For example, when you are using a blade, like diamond blade, you want to have a single crystalline material. But most of our materials, as I told you, have polycrystalline structures. And then it really depends on the grain distribution and the grain size if the material is going to be isotropic or anisotropic. For example, here, this is a picture of a material. I forgot which material it is. But here you see that the grains are randomly distributed. So it doesn't matter if you are stretching in this direction or the other direction, you are going to get the same stiffness. Yeah? But here, the grains are completely elongated, preferred in some preferred directions. In these situations, it matters a lot if you are pulling in the direction of the elongation or perpendicular. So you are going to have anisotropy. So this is important that you kind of see how the crystalline structure also relates to anisotropy and isotropy of the material. We talk a little bit more about polycrystalline materials later. I don't have time to talk today. So let's do just some examples I picked up from Fundamentals of Engineering exam, and just do them one by one together. So, yeah, starting with this one. Yes, exactly. So this is this other illustration. That's why I told you it's good to, yeah. So it's good to see, yeah, I see a few correct answers. That's what I'm here.
What's the best way to start?
So the best way is shared with how many cells. So imagine this. This is just a cube, and there are cubes all over. Let's just start with this one. This is convinced. Yes. So the answer is 2. But be convinced. Convinced. It's 2. So I was just explaining to one of your friends, the best way to imagine this is to think that this unit cell is a Lego block. So you all know what Lego is, right? So you are putting this next to other blocks. And just think how many atoms, how many other blocks share each one of these atoms. So for example, the middle one is only going to be shared by the block that you put on top of this, right? So 1/2 of it belongs to this unit cell. You have 2, so it will be 2 times 1/2. The corner ones are going to be shared by 8. Because you are going to put 1 here, 1 here, 1 here, 1 on the top. So it's going to be 8. Try to imagine this. Yes? We have 8 of that. 1, 8. I tried to draw something, but it may not come out very good. So this is what I mean. Like, try to imagine all the blocks that, and of course there is one in front and one here. So I told you that it's not going to be good, but this is what I mean when I say it's the building block. Okay? So this one is neither of the crystalline structures that we have talked about. It is a different one, but you should be able to answer these questions without any problem. Now the next one. Try to look at, I have a nice demonstration for this hexagonal closed patch. It's hard to imagine, look at that illustration in a few previous slides, because I would not be able to draw it. I've seen one correct answer. So let me go back to just the demonstration of the hexagonal. Yeah, so this is how it would look like. So it's a little bit more complicated. And each one of them is going to be shared by 6 neighboring blocks, which look exactly the same. Now we don't have these ones in the middle anymore. So basically we have 12 and the other 2 on the face. It's just 3. Next. So as I said, these are from fundamentals of engineering. I haven't changed anything. If you are okay with the previous one, please continue working on this one. But if you are not okay, maybe I could have explained this a little bit better. So if you look at one corner one, it's complicated. So, like, if you consider there are like 3 of them in this level, and then we can put 3 on the top. I don't know how else to draw this. So this is like the 3, and then you put 3 on the top. This is going to be shared by all 6. And you can say the same thing for any of the corner ones. Yes? Makes better sense. Yeah. So this one, pay attention that this is not a cube. So I don't know why they have given this in the exam, but this is what they have given. Yeah. Let me see. It's correct. I've seen one correct answer. That's just it. So you need to go back to the definition of APF, which, remember I told you, it means how much of the volume is filled with atoms. So you just divide the volume of the atoms in your unit cell. So we have two whole atoms right here. And each one of them, the volume is the volume of a sphere. And the unit cell, it is not cubic, so, but the dimensions are given. So it's kind of a little bit different. And I think if you do the calculations, you are going to get this number. If you have no questions about that, then the next problem. And this one we solved in the class, so I just this is the simple cube structure, the first thing we did in the class yesterday. So I guess we can go back and check, but it is simple because A is 2R and you only have one whole atom. Yeah, I just keep it for another 20 seconds, but work on the next one if you have no questions about this one. Use the relationship between R and A for VCC crystal, which is, this is how I remember it. And then here A is given 2.86 angstrom, and then you can calculate R. That's straightforward. I hope that you know like how to get the relationship without memorizing it. That would be great. If one day you took the fundamentals of engineering exam and you had to solve a problem like that. Any question? We move from this one. And the last one. This is somewhat you need to kind of know. But if you look at the table, try to look at the table that I showed you and find the right answer. It's crystal. No, it's crystal. So the answer is sodium, of course, but so I have the new handouts, but it's Friday before spring break, so I give you the handouts, but I guess we don't start the new handouts on Friday. But I've carried them here, so believe me, I have 15 minutes, and these are pretty heavy. So let's see if there is enough for. So have a very nice break. Have some fun. There is a quiz on the Monday after the spring break. But the exam needs to move later time. So don't worry about the exam. I sent you I do not know because I want us to finish the series before you have the exam. I just cannot it's hard. But I try to let you know at least 1 week in advance, so it won't be like, okay, tomorrow. Have a really nice break. Enjoy, stay out of trouble. There are the extra topics. Please remember to bring the new handout with you. Remember to bring this next time.